Okay, guys, welcome. Today we're going to talk about probability. Now, in this first video, we're going to talk about a lot of definitions and some basic principles that involve probability. Okay, so to start off, we have that an experiment is some sort of procedure that will lead to certain outcomes. And this is sort of like the most basic thing that we start with. Now, an outcome is the most basic result of an experiment, right? So an outcome can be any individual occurrence of some type of result of an experiment. Now, an event could be made up of one or more outcomes that make up some point of interest, right? So as an example, we'll say that the experiment would be tossing two coins. So then your possible outcomes are to get both heads, then or both tails, or you could have a head and then a tail, and then a tail and then a head. Now, for example, an event could be what are the number of heads that come up, right? So you could either get 0 heads, 1 heads, or 2 heads. And here, of course, heads, tails, and tails, heads would correspond to the same event, right? Because they would both correspond to 1 head happening, right? So that's sort of the distinction between an experiment and then outcomes and events. Now, a sample space, which we'll call a capital S here, is the set of all possible outcomes of an experiment. So if you have outcomes S1 through SK, then we say that our sample space is just the set of those S1 through SK. Now, the intersection of two events corresponds to the event that both occur at the same time, right? So if you have that your experiment is rolling a single die, and the sample space, well, not the sample space, but the event E is the event of an even number coming up, and L is the event of a 4, 5, or 6 coming up, then the intersection of these two events would be, of course, both events have a 4 and both events have a 6. So that would mean that the number is even and it's also 4, 5, or 6. So it would have to be 4 or 6. Now, we say that two events are called mutually exclusive if they cannot occur together, right? So if we have the set O, which is 1, 3, 5, and our set from before E, which is 2, 4, 6, they would be mutually exclusive because they can't occur together, right? One's the even numbers, one's the odd numbers, and their intersection, of course, is the empty set, right? So we would say that those two events would be mutually exclusive. Now, the union of two events would indicate the event where either one or the other, or I guess technically both, would happen, right? So you could have, if you take even union with L, then of course we could have 2, 4, 6, and we could have 4, 5, or 6. So that's where you're seeing all those numbers sort of appear there. Okay. So now what we're going to do is we're going to talk about how to come up with a probability space or a probability distribution. Now we're going to let our sample space S, consisting of outcomes S1 through SK, be the set of all possible outcomes of an experiment. Now, to get a probability space, we assume that each outcome SI has some probability, which we'll call P of SI, such that all of our probabilities are non-negative, right? So greater than or equal to 0. And the sum of all these probabilities would have to sum to 1, right? So then we call S together with these probabilities a probability space, right? And of course, a very simple example would be that tossing a fair coin, right? So you have 1/2 chance of getting either heads or tails, and that essentially sums up everything, right? Because that 1/2 probability, of course, is non-negative. And if you add probability of heads plus the probability of tails, you're of course going to get 1 because you have 1/2 plus 1/2. Now, for the most part in this course, we're going to consider a simple type of probability space, and that will be the probability space where each outcome has the same probability of occurring. And we call that a uniform probability space. Okay. Now the probability of an event A, which is a subset of our sample space, is defined as the sum of probabilities of outcomes in A, right? So the sum of probabilities that would make up that certain event. And for a uniform probability space, the probability of that event is the size of that subset of the event that we're interested in divided by the size of the sample space. All right, so let's do a couple of examples of that. So now, as an experiment, we'll say that we're rolling a single die, and the probability, or sorry, the event E will denote throwing an even number, and T will denote throwing a number that's divisible by 3, right? So our E here would, of course, be 2, 4, and 6. And our event T, number divisible by 3, would either be 3 or 6. So now the probability of E would be equal to the size of E over the size of S, and of course that would be a 3 over 6, right? Or you could even say that it's 1/2. Right, now for T, same idea. We want the size of T over the size of S. Now the size of T is just 2, and S is still 6, so that would be 1 over 3. Now for part C, we want the probability of E union T, right? So E union T is that it's even or divisible by 3, right? So first of all, EUT would be 2, 3, 4, and 6, right? So the probability of E union T would be 4 over 6, or 2/3. Okay, and then finally for part D, if we wanted E intersect T, that would be that it's even and divisible by 6, and that would of course just give us one event there, that would just be 6. So of course the probability of E intersect T would be a 1 over 6. Okay, so that's the idea. Now we're going to show two examples that are sort of some nice results here, and I believe that's and then that will conclude this video. Now the first example, we have that if A and B are exclusive or mutually exclusive, then the probability of A plus the probability of B will give us the probability of A union B. Now let's think about what it means if A and B are mutually exclusive. Well, that means that A intersect B is the empty set, and of course the probability of A intersect B would be 0. Okay, now one way that we can think of this is we can use sort of a Venn diagram approach. If our events are mutually exclusive, then there's no overlap, right? Then we have something like this. So it seems clear that if I want A union B, I would just have A and then add it to B, right? So this is sort of the Venn diagram proof is sort of obvious. Right, now I think it will be easier to see this proof now, and then we can sort of talk about how you can modify the argument for if they are exclusive. Okay, so now we're talking about any events A and B, not necessarily mutually exclusive. So now we could have overlap. Okay, so now we're saying that the probability of A intersect B plus the probability of A union B would give us A plus B. Now the probability of A intersect B, or A intersect B, just the region is of course right here, right? Now the probability of A union B, which we'll do in purple, is everything, right? So it's all of A plus all of B. right? So it looks like I've counted the middle part twice because I have the red stripes and then I also have the purple stripes. And of course, that would also occur if you were to take A, this entire region here, and then add that to B, of course, this entire region here, because then you would count the middle twice again. So that's one way you could sort of easily show this. Now, another way that you could show this is to break this up into a couple different regions, right? So another approach is to look at it this way. Come on. Okay, there we go. So another approach is to look at it this way. Okay, we're going to call this part here A minus B. Okay, and then of course we'll call this part here B minus A. Okay, and then of course what we have left is the intersection, right? In this middle part. That's where we have A intersect B. Right, now you can see that A union B would of course be A minus B union with A intersect B union with B minus A. Right, and of course A intersect B is just A intersect B. So it looks like we could say that A is A minus B union with A intersect B, and that B is A intersect B union with B minus A. Okay, so we've sort of broke everything into these chunks. Now remember that what we're trying to show is that the probability of A intersect B plus the probability of A union B is equal to probability of A plus probability of B. Right? Well, now let's replace what we have for some of these things. Now, probability of A intersect B, we'll just say probability of A intersect B. But I can say that probability of A union B is the probability of A minus B plus the probability of A intersect B plus the probability of B minus A. And that equals probability of A, which is the probability of A minus B, plus the probability of A intersect B. And the probability of B is probability of A intersect B, plus the probability of B minus A. Well, now if you look at the left and right-hand sides, you have the same thing because you have a probability of A minus B and a probability of B minus A on both sides, and then you have two probability of A intersect B on both sides. Right, so it might be a little bit confusing, but once you sort of write out the Venn diagram and sort of break it into these disjoint sections, you can sort of show it very easily. All right, so that concludes this first video on an introduction to probability. I hope you enjoyed, and I will see you next time.